Space has many mysteries, but imagine holding a teaspoon of material that weighs as much as 10 million tons, equivalent to the weight of about 3,000 Empire State Buildings. This isn't science fiction, it's the mind-boggling reality of neutron stars, the universe's cosmic crushers. These stellar remnants represent one of the most extreme states of matter known to science, where the fundamental forces of nature are pushed to their limits. To appreciate just how dense neutron stars are, let's start with something familiar: Earth. The average density of our planet is about 5.5 grams per cubic centimeter. Now, imagine a star like our Sun reaching the end of its life. After exhausting its nuclear fuel, it sheds its outer layers and collapses into a white dwarf. The typical density is 1 million grams per cubic centimeters, meaning a sugar cube-sized piece would weigh about 1 ton on Earth. This dense material is composed primarily of electron degenerate matter, which supports it against further collapse by electron degeneracy pressure. But this is just the beginning of our density journey. When a more massive star undergoes a supernova explosion, something even more extreme can form: a neutron star. Their typical density is 10 to the power of 17 grams per cubic centimeter, meaning a teaspoon of neutron star material weighs approximately 10 million tons. This would be the entire mass of the Sun compressed into a sphere just 12 miles in diameter, which is so dense that the atomic structure completely collapses. Protons and electrons merge to form neutrons. To put this in perspective, if you could somehow transport a marble-sized piece of neutron star material to Earth, it would punch through our planet like it was made of tissue paper, cutting all the way through to the other side and beyond. Leave a like if you've enjoyed it thus far. So what happens to matter at this density? At the surface of a neutron star, gravity is about 2 billion times stronger than Earth's gravity. This creates conditions unlike anywhere else in the universe. Normal atoms cannot exist because of the immense pressure, which forces electrons to combine with protons, creating neutrons. This quantum mechanical effect prevents neutrons from occupying the same energy states, creating an outward pressure that counteracts gravity. In the core, densities may become so extreme that neutrons themselves break down into their constituent quarks, potentially forming what physicists call quark matter, or strange matter. One theory suggests that the neutrons in a neutron star's interior may form a superfluid, a state of matter with zero viscosity that can flow without any friction. Neutron stars don't just sit there being dense, they spin at mind-boggling speeds. Conservation of angular momentum causes this extreme rotation, like a figure skater pulling in their arms.